Hello everyone, welcome back to our channel Maxcotech. You are watching series Wireless Census Networks. This is the seventh part of the series in which we are going to look at data collection gossip logarithms. This video is going to cover following topics. First, we need to answer why do we need a new logarithm. For that, we are going to look at the major disadvantages of loading and tree-based logarithm and see if gossip logarithm is going to fulfill these. Then we will look at the goals what gossip logarithm solves. And then finally proceeding with the definition and the example of gossip logarithm. We'll study about its properties and a basic model. Then we will know the difference between node-based gossip logarithm as well as the edge-based gossip logarithm. We'll also study about the mass conversation property, which is like all of the nodes have to come to a common state in the end of the execution known as consensus. Then looking at some properties including time complexity and message complexity. And finally, we'll look at how and where this gossip logarithm is being used in real world examples. And in the end, finally, we are going to conclude by looking at the advantages and the disadvantages of gossip logarithm. So let's get started.
So let us first answer ourselves, why do we need gossip logarithm and why do they exist? What problem this logarithm solves? Um, so the problem of the data collection and the propagation is simple. Allow the message M to be received by all nodes in a network as fast and as efficient as possible. What floating offers is that sync node sends the message to all of its neighbor nodes. Then every informed node forwards it to all of its neighbors. The disadvantage here was that it has high communication cost. Every node needs to interact with all other neighbor nodes, and every node could possibly receive two copies of the message in the worst case. And what tree-based logarithm offers is that constructing a spanning tree and spreading the message on the tree edges. The biggest disadvantage for this one was it is fragile, as we studied before, and it is not robust because it cannot tolerate link failures. And if any of the link failure happens in any edge, it destroys the complete chain of the nodes. So we need such a logarithm that fulfills our goal stated earlier. Such logarithm for information spreading that is simple to implement, it is local. By that I mean no need for every node to store the data about the entire network. It will save the node's memory and hence the overall cost. Distributed, so no need for each node to communicate among all other nodes. It should be robust, it could tolerate the link failures, etc. And yet it should be fast. Now all of these properties are almost fulfilled by this gossip logarithm. How? We are going to look at that now. So the formal definition can be described as information is spreaded in pairwise operation of the nodes. So let's say a node I selects any of its neighbor node at random and then it passes the message to that neighbor node. So these two steps make one complete round. So examples include analyzing of community structure, computer virus, help building better networks, analysis of a spread of a virus, fake news in an election, etc. And as you can see, the picture described here is exactly the literal meaning of how this gossip logarithm was named after. So looking at the properties of this logarithm, every node periodically exchanges the information with any of its neighbor node. Selecting a node at random and exchanging the information equals one round. Next round for every node starts at the equal probability among every other node. So all nodes gets the equal chance of participating in gossip event. So here is the simple model of this logarithm where the value of node P at time t is represented as small x p t, where small x is the subset of the capital X, which could have any of the value of the capital X. Let's say in this case 1, 2, 3 till n. And the value of the same node at the next round, t plus 1, is represented as function of the node P last value and the neighbor node u current value, where u is one of the neighbor node of the node p. Describing this model in a graph, here how it looks like. Um, so at time t, let's say the value of node p at time t was 2, value of node u, which is one of the neighbor of p, is 3. And in the next round, if we say our function was max, it first calculates the max of both of these values, and the final value is then updated in node p. So basically node P has exchanged its value from node U based on an operation max. So we have further two types of logarithms under this category. The first one is node based and the second one is edge based. The only difference is that in the node base, a node is triggered uniformly at random, whereas in edge, an edge PU is triggered uniformly at random. Looking at the node 1, after the node P has been triggered uniformly at random, P randomly selects one of its neighbor, U, which is a subset of all of the neighbor sets of P. Then after that, P exchanges the value from U at the next time slot. Whereas in edge base, after an edge is triggered uniformly at random, both of the nodes updates their value at the next time slot. In our next examples, we will be mostly talking about the node-based logarithm. So what is mass convergence in gossip-based logarithm? State of all nodes converges to a common state at the end of the execution. So let's say in a connected graph, finding the average from all nodes at the initial time t0, the average of all nodes will eventually be equal to the final time where the execution ends. The average of each value in all of the nodes in a network at the initial time t0 will always be equal to the average of the values of all the nodes in a given network at time tk, where tk is considered to be as the last time where all the nodes meet at a common state. At this time, all the total average is always the same with high probability of 1. So by convergence, I mean that every node in a network must decide in a common agreement. And when they do, the execution ends and we have reached convergence. Consider a distributed system with n nodes. Each node I has an input xi. A solution for consensus problem must guarantee the following three statements. The first one is all healthy nodes must decide on the same value, which is called agreement. The decided value must be the initial input of at least one of the healthy node, which allows us to give the validity of this final common state of the network. And to determine the termination, we have to be sure that every healthy node has eventually decided on any of the value. By fulfilling all of these properties, we have reached consensus. Looking at the time complexity here, we would describe it as the time required for the message M to be received by all nodes. Let us look at the line graph. Time t to wait for its activation is a geometric random variable of parameter. So at time slot t1, probability of edge e12 to get activated is 1 over n. At the time slot t2, the probability of the same edge would reduce down to 1 over n plus 1. This is because at this time t2, we now have same probability as above in time t1, but along with that, the algorithm can also activate the same edge again. So we have n plus 1 possibilities of edges getting active. Once information is spread to the node 2, we then have to wait for the edge E23 to activate at the time T23. This T23 is the time to wait to see the activation of the edge 23, which is geometrically random variable of the parameter 1 over n. So the total convergence time T will eventually be the sum of all of the times taken by every single edge to get activated. Hence the time complexity is O n square. And looking at the properties of other topologies of the graph, we have n to the power log complexity for complete graph, and for the grid, the time complexity would exactly be proportional to the number of nodes. So gossip logarithm message complexity, which defines that how many times a message m will circulate in a, let's say, complete graph before it reaches all of the nodes. So let IT be the set of informed nodes at the end of the round t, and let UT be the set of uninformed nodes at the end of round t. So to understand this execution, we will kind of split it up into three phases, whereas in the first one, uh, the informed nodes are very, very less than the uninformed nodes. In this case, we will have high probability of informed nodes spreading message M to uninformed nodes. So the number of informed nodes doubles after each round. Reaching at phase 2, where we could say that informed and uninformed nodes are nearly equal. In this scenario, we already have a lot of informed nodes, so the rate of number of informed nodes will increase slowly. And in the third phase, we now have higher number of informed nodes as compared to the uninformed nodes. So there will be few non-informed nodes left. So rate of the non-informed nodes decreases. So the message complexity for the complete graph is logarithmic in nature with number of nodes. And for the line and ring graph, it's n to the power 3 and n to the power 2 for the grid, where n is the number of nodes. Some of the real-world applications of this gossip logarithm is Amazon, where it uses gossip protocols to quickly spread informations throughout the S3 system. Amazon Dynamo uses a gossip-based failure detection service. BitTorrent uses gossip to discover nodes in peer-to-peer network, and it's also used in smart farmings to run the same logarithm on nodes to aggregate data and report them back to the central hub. So we do have pretty much advantages of this logarithm as we studied earlier. It is indeed simple to implement. It is highly robust against node failures and against any changes in the topology in the runtime. It is capable of self-stabilization. So if any node or any edge in between two nodes fail, it still is capable of spreading the same message across all of the network. It is fully distributed because it uses pairwise operation, and nodes not need to be aware of all of the nodes in the network, only their neighbors. So they use local information only to spread the rumor across the network. It does uses small messages, due to which it has low communication bandwidth. Some of the disadvantages, as you can imagine, for this logarithm are when a rumor is spread across multiple people, um, the original message of the rumor doesn't stays the same. So the final results obtained are probabilistic in nature. So it is always ideal to use this logarithm in a really large wireless census networks to obtain high probability of accurate results.
So with that, we have completed all the three types of data collection logarithms: floating, tree-based, as well as the gossip logarithm. Now in the next videos of this series, we are going to implement all of this theoretical knowledge that we have studied in the real world projects by building peer-to-peer network based on ESP32 as well as ESP8266. That is all for this video. I hope it was informative for you guys. And if it was, please don't forget to thumbs up, leave a comment by sharing your thoughts as well as any questions. Subscribe to our channel if you are new here. This is going to keep us motivated to bring such useful stuff to you guys in the future. So stay tuned for my upcoming videos. Till then, I will see you in the next one. Take care. Bye.